Hello and welcome to the second part of these talks about electric and magnetic fields. This time I want to introduce a different way of thinking about fields and the concept of potential. And I'm going to use the gravitational field and the weight of objects as the example because that's one that we're all familiar with. So, back to gravity. Gravity is a force which attracts any two objects with mass. Any two objects with mass, there's a force attracting them together, and that's called gravity. The force on those objects is known as their weight. And weight is a vector field. It has a value and a direction at all points in space. But there's another way of thinking about gravity, and that's in terms of a gravitational field. This is slightly different from a scalar field or a vector field. Both of those are just ways of saying that there is a quantity that takes a different value anywhere in space. You can think of the gravitational field as being something that just exists throughout all of the volume of space. And what it does is it stores energy. For example, this pen here. This pen has a weight on it, which is a force of attraction pushing it down towards the Earth. In order to keep this pen stationary, I am having to exert an equal and opposite force pushing up on it to cancel out the force of its weight pushing down. Now, if I lift this pen up, I'm having to do work. The force that I'm exerting on this pen, the force that I'm exerting on this pen is going through a distance, and force times distance is work. So I'm doing work, which means that I'm losing energy. If I'm losing energy, where does that energy go? We know that energy is conserved, but where is it? Well, the pen here and the pen up here, they have the same mass, they have the same size, they're at the same temperature. Where did that energy go? And one way of thinking about this is that that energy got stored in the gravitational field. Now we can work out exactly how much energy is in a gravitational field by considering a simple example. Let's consider we have an object of mass m1 at this point in space. And it's fixed at that point in space. And then we have a movable mass of m2, which can move. And it's coming from an infinite distance away to end up at this point here, which was a distance r away from m1. Now, there is a force, the gravitational force, attracting that mass towards this fixed mass m1. And the object is moving in the direction of that force, which means that the force is doing work. So whatever is exerting the force, in this case gravity, is losing energy. And that energy is coming out of the gravitational field. How much energy has to come out of the gravitational field to get this mass m2 from an infinite distance away to this point here, r? Well, Newton showed that the gravitational force is a constant called big G times the product of the masses of the two objects divided by the square of their distance apart. Now, unfortunately, we can't just take the force on this mass and multiply it by the distance that it's travelling, because the force isn't constant. The force is a function of how far the two masses are apart. What we have to do is consider just a small distance. I'll call it ds. From there to there. And it is a distance s away from where m1 is. And if ds is an infinitesimally small distance, then I can assume that the force will be constant over that small distance ds. So I could determine how much work is done in order to get the mass from this point here to this point here, just moving a distance ds. That I will call dw, the small amount of work done to get it from there to there. Well, that's equal to the force times the distance. The force at this point here, where the two masses are a distance s apart, is g m1 m2 over s squared. And the distance, well, the small distance that m2 has moved from here to here is minus ds. And it's minus ds because the distance s is decreasing. It's going from here to here, so the distance decreases. We need to multiply by minus ds to get from there to there. All we need to do now is to integrate this, which effectively adds up the small amount of work being done to get the mass from all of the tiny little distances from infinity to this final point here, a distance r away from m1. So we have the integral of, from 0 to the total work done, dw, of g m1 m2 over s squared times minus ds from infinity, where it starts, to r, where it ends. Now, g, m1 and m2 are all constants, so we could just write this as minus g m1 m2 times the integral from infinity to r of ds over s squared. The integral of 1 over s squared is minus 1 over s, so that would end up with g m1 m2 times 1 over s from r to infinity, and that is just g m1 m2 1 over r 1 over infinity. 1 over infinity is 0, so we just end up with g m1 m2 over r. That is the total work done by the gravitational force to get this mass m2 from infinity to a distance r away from m1. And that is energy that comes out of the gravitational field when that object is moving to that distance r. We can take this result and derive a very useful quantity called the gravitational potential. The work done by the gravitational field, W, is g m1 m2 over r in getting the two masses a distance r apart from being an infinite distance apart. That means this is the energy that is lost by the gravitational field. So the change in the energy of the gravitational field, if it's lost that much energy, the change in the energy, I could write it delta E, is minus g m1 m2 over r. Negative because this is a loss of energy. The gravitational field has given up energy to do this. The final stage is to say what is the change in energy if m2 is a unit mass, 1 kilogram. We'd write it as Vg, the change in energy of the gravitational field due to moving a unit mass from infinity to a distance r away from a mass m1 is minus g m1 over r. And we call that the gravitational potential. And that makes calculations to do with gravity much simpler to do, as we'll find out in the next video.